Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so let's start. So it's my pleasure to introduce Sylvain Klevsch, who has a ton of industrial experience about distributed programming, and who is also completing his PhD at Imperial College, and is going to tell us all about the Pony programming language. Sylvain.
Thank you. First of all, thank you everyone for coming. I really appreciate it. Whoa, sorry. So I'm going to talk a little bit about Pony today. My background is I've been an industry programmer for too long and worked on too many things. Most recently has been in the finance industry, which is a strange and wild industry. And all of these things that I've worked on for my career have some things in common. First of all is that they're performance critical and they benefit from concurrency, which is pretty straightforward. The other is that most of them are actually distributed systems, even if I didn't know that when I was writing them, which is sometimes problematic in hindsight. So my current work is on Pony, which is an actor model language, native language, and it's designed to scratch my own itch. Basically, this is a language that I wish I'd been programming in for the last 24 years. So I'm going to dive right in. I'm going to cover mostly type system stuff and garbage collector stuff that's interesting towards the distributed computing work on Pony that I'm doing now. Some of you might get a little bored. There are people in this audience where their work is foundational to Pony. So I hope you don't get too bored. So let's start with this. This is about the simplest program you're going to write in Pony. It's the straightforward program. Let's talk first a little about the goals. Statically data erase free, but with mutability. No stop the world garbage collection is really important. That's a performance bottleneck for a lot of systems these days. Formally specified, that's not the same thing as formally verified, of course. I'd love to get into verification work, but that's not where Pony is yet. Single node performance needs to be competitive or beat C and C++. That's actually in the bag. That's something we've nailed. Distributed computing is really our next step, is being able to scale this across clusters with a single program. So people often ask me, what are some types of programs you'd like to write in Pony? And the answer is gigantic list, right? Some of these are things that I've written that I wish I'd written in Pony, video games particularly. Other is stuff that I have actually already written in Pony. There are financial systems written in Pony, stream processing systems in Pony, quite a bit of low-power device software written in Pony, interestingly. So, as I said before, there's a lot in Pony. It's actually in production. It's not just an academic language. So that means there's a lot of things I'm not going to talk about today, but hopefully this is all stuff that most of you would take for granted anyway. Generics, intersection types, various types of subtyping, pattern matching. But some of the stuff in the runtime that I won't touch on, unfortunately, is things like scheduling, work stealing, things like that. But I will touch on the garbage collector. So we're going to walk through quick some of the things in that example. So the first is, we'll see that when we created the main actor to start the program, we passed in an environment. And that's because Pony is a capability-secure language. We have no global state, and the possession of an address, the possession of a reference to an object, is the authority to use that object, right? And that means to avoid ambient authority, where that authority permeates a program, it means everything has to be explicitly passed to the user. So standard out is part of the environment, and if we want to print the standard out, we're going to have an environment to print to. So capability security is an operating system concept that comes from the 60s. It hasn't maybe gotten as much press as it deserves. Mark Miller has probably been the most prolific author on object capabilities lately. But it really expanded to languages with E and ambient talk and Caja. Now SES on JavaScript is implementing object capabilities in JavaScript, which should be pretty interesting. Caja did that as well, but in a much more restricted way. So Pony is an OCAP language, and is an OCAP for the initial environment, which is pretty straightforward. But what Pony does that's very different from these languages is reference capabilities. Object capabilities are about security and authority, but they're not about data race freedom or any of these other interesting properties. So, for example, the immutability of the environment is a reference capability in Pony. And I'll expand on this as I go. So the actor model and Vout is an actor. It encapsulates standard out. So we're going to, instead of locking or anything like that, we're going to send a message. We're going to print by sending the message print and sending the string hello Cambridge. Straightforward stuff. Simple message passing. So this all comes from a long history of actor model research. Carl Hewitt, Cedric, who's sitting right there. And the other languages that are actor model are, yeah, sure, Erlang, E, ambient talk, JavaScript. JavaScript is an actor model language, as well as lots of actor model libraries. So, I'm actually stop here for a second. One of the big things you'll see is that we don't see a lot of type-safe native languages on this list, which is interesting. That's not been something that's been explored very much. So, why is it safe to send a string? Because it's immutable, right? It's a globally immutable string literal. In this case, that's val. The type of it is string val. And it's safe to send those because there are no data races on immutable data. That's great. But we want to be able to send mutable data. So here's an example. This is examples from the standard library mostly. So this is a TCP connection. And a TCP connection needs a notifier. And that may actually contain mutable state because you're doing stateful protocol decoding, for example. So we need to be able to pass in something that's isolated. It needs to be mutable, but we need to be certain that no other actor is going to be able to read from it or write to it, or else it wouldn't be safe for us to write to it. So that's good. Isolation for data race, free, mutability, straightforward. We can send it in a message because of the guarantee that there are no other aliases to this that allow reading and writing. And aliasing is the real key behind reference capabilities. There's another thing that we could send in a message. We could send a tag. We could send the identity of an object without the capability to either read from it or write to it. And a classic example of this is an operating system's set of hierarchical timing wheels, right? Where you need O1 cancel on timers. It's critical for performance. So I'm going to send in an isolated timer that needs to have the possibility of having mutable state. It may not need it, but it needs to have the possibility of having mutable state that it can mutate when a timer fires, but you want to be able to do O1 cancel. So you want to be able to refer to that timer by identity later and ask for a cancel. This is safe too, right? To send a tag in a message because we're not allowing read and write. And a tag is compatible with an ISO. You can have an alias of an ISO as a tag. It's because it doesn't allow reading or writing to the object. So an opaque reference isn't going to be the source of a data race. So that's good. We can also type actors using tag. So sending an asynchronous message to something is not reading from it and it isn't writing to it. So it's safe to do that with identity only. And that's quite interesting because it means that the actors themselves, your units of execution, are actually part of your reference capabilities type system. So here we see an example of a behavior, which is an asynchronous method, B, and it executes. But something interesting here is when you receive that message, now you're typed as ref, a mutable type, sort of a standard object-oriented language style mutable type, except with the guarantee that you know that no other actor is going to be able to read from or write to that instance. And so the actor can go ahead and mutate its state and do everything it needs to do, very typical actor model programming, safely. So the golden rule of data race freedom, right? If I can write to it, nobody else can read from it. And the corollary, if I can read from it, nobody else can write to it. That's good. There's a lot of existing data race freedom work. This is a lovely field with lots of good stuff happening. Pony is not invalidating any of this work, right? It's building on all of this. Probably the papers that have been most important are the three at the top. The others are much more restrictive in the way that they treat isolated state, in the sense of requiring a certain shape to the data. So one of the big differences is that Pony's reference capabilities are built on the concept of denying rather than allowing. So instead of saying this is a capability and it lets you do this set of things, it says the existence of this alias means that there are other aliases that we know can't possibly exist. And it appears to be that maybe this is more fundamental than permissions. So here's the matrix. This is great fun. So here we've got the things that we're going to deny globally and the things that we're going to deny locally. And you'll see that some of these are empty because we can't deny locally what we allow globally. Local execution is a part of global execution. And there's some properties. Before I actually talk about the reference capabilities, I want to talk about the emergent properties because they're pretty interesting. If you can deny global read and write aliases, then you're mutable, right? It's safe for you to mutate because you know no other unit of execution, no other actor is going to be reading from that. So you will still maintain data consistency, right? Not just data race freedom, but complete consistency. Similarly, if you know that you deny global write aliases, then you have a form of immutability. It may be global immutability, in which case that's great. This is an actual proper immutable object. Or it may simply be local immutability, meaning I can't mutate through this alias, but I can't guarantee you that there isn't some other alias held by the same actor that could mutate the object. I can guarantee you there isn't one held by a different actor. So that's sort of like a C++ const style behavior, where you're saying, I'm not going to change it here, but God knows what's going to happen elsewhere. All right. And then the last one is opaque. If I can't make any guarantees, then this is just a capability token. The other one is these ones in italics on the diagonal here. So in that little intro on some different message types that are sent, everything that's sent is on the diagonal. And it turns out when you deny locally the same that you deny globally, then you can send that alias, that reference in a message. Yeah?
So these things are like qualifiers on types?
Absolutely, they're type annotations.
So when I declare a new variable, for example, I say, well, it's one of these things, right?
Yeah, absolutely, yeah.
When I declare a new data structure,
yes.
and I want to say something about the permissions and ownership inside the data structure.
Yes.
How do I use these qualifiers, or I don't use these qualifiers?
You do, exactly. So every reference, that's why it's called reference capability. That's an excellent question. So that's why it's reference capabilities. Every reference has one of these annotations.
So when I declare at the declaration side of a data structure, I use these.
So a data structure does not inherently have a capability on the outside of it. So a class doesn't inherently have a capability. I could have an isolated instance of it or an immutable instance of it, but it's fields.
So does the field have a? That's what
yes, absolutely. Yes. So the field has one, and this leads into something that I'll talk about in a little bit, which is viewpoint adaptation. That's a fantastic question because this is very important for the idea of saying, how do I see something that's inside some other data structure? Because the reference capability that I'm looking through is critical to that, right? It's going to modify it all the way through. Absolutely. Thank you. All right. So, and then it turns out that we end up with a set of 6 reference capabilities. As far as I can tell, these are fundamental. It'll be fun and interesting to find out over time whether that's really true or not. So isolation, immutability, and opaqueness are pretty straightforward. Ref is straightforward too, a mutable object. And box, while relatively horribly named, is still pretty straightforward. It's a black box. You can read from it, but that's all you know about it. You can't make any other guarantees about it. And I'll show you why on the next slide. Transition appears to be a new form of uniqueness, which is write unique as opposed to read and write unique. At first, I thought that this was essentially a useless capability. And I've since been shown by other Pony programmers that it's quite useful indeed to have something that's write unique but not read unique, which is very interesting. So, talking about box for a second, Adrian Collier writes a great blog called The Morning Paper where he does a review of an academic paper every single day. It's pretty astounding. And he did a few reviews on some Pony papers. And he covered the reference capability type system. And he drew this himself. And I asked him very nicely if I could use it in my future talks. And he agreed. What he did was puzzle out something that I'd failed to put in the paper, that had been in my initial work but hadn't been in the paper, which is the concept of compatibility. Given some alias, what aliases are compatible with it? And this is fairly straightforward. If you have something isolated, you're not going to be compatible with anything except a tag, right? It's not that complicated. If you have something that's globally immutable, there's going to be no way to write to it. The really fun bit is box. That it's certainly compatible with local read aliases, and it's certainly compatible with tag aliases. Yeah.
Compatible, you mean I can write to one a value of the other?
I'm sorry. Yeah, so compatibility, I'm sorry, thank you. Compatibility meaning it is possible for these aliases to exist in your program simultaneously.
Correct, okay.
Yeah. Yeah. So for box,
at a particular moment in time. But they could, it doesn't
Right.
matter whether they could exist. One could exist at one moment and
correct,
the same
absolutely, yes, at a particular moment in time. Because I might have something isolated and then give up some of those deny properties and make it globally immutable, make it a val type. So they may, at different points of time, exist, but at a given point of time, you can be statically sure that only compatible aliases to the same object exist without introducing reasoning by time. So, right, so box is either compatible with something that's globally immutable or compatible with something that's locally mutable, but never both simultaneously. And it turns out a lot of the code you write wants to deal with references in exactly that way. So, viewpoint adaptation. Coming to the question. So, viewpoint adaptation is just a question of, as was said, that you need to be able to look through an object and see something. And here we have a sort of an interesting type. This is another example from the standard library, which is how you pull something out of a hash map, where the key here is how some readable type sees the key. And not only that, it's an alias of the type that a readable type would see when it sees the key. And that ability to specify aliasing and unaliasing directly in the type turns out to be pretty powerful in terms of writing complex standard libraries. And similarly, it returns a value that's modified by the receiver. Now in this case, because we haven't specified a type, a capability for the receiver, you can put one right in between the keyword fun and the name of the method. It defaults to box. So we're going to say, this is something that we can do on any readable type, and it's going to return us something that as it's modified by the receiver. Just an annotation note, this is a partial function because there might not be something in the range for the element in the domain, and that's how Pony deals with exceptions, is to consider them partial functions. So, if you can do aliasing, you also want to be able to talk about unaliasing. That this is the type if an alias to it were destroyed. In a concrete sense, that's most useful for the unique types, read and write unique isolation and write unique transition types, because it lets you say, not only is this object isolated, but I have consumed the isolated reference that I had. So I'm passing one that if you assign it to something, it remains isolated, which is a big distinction to saying, I'm simply passing you a reference to something that's isolated, but if you assign it to anything and alias it, you're going to get a tag. You're going to get an opaque reference. So for example, when we update a map and we get the old value, we get an ephemeral with the little hat of the value in the map, or possibly none if there was nothing in there. It's an algebraic data type system under the hood. I often tell people that Pony is object-oriented because it makes them comfortable. It's essentially a functional language. So here's an example of ephemerality and what I mean by saying what you can assign. So here we have some ant and a hash map of aardvarks, and we're going to look up Bob, and we're going to give Bob an ant to eat. And that's fine, because even though this is a collection of isolated aardvarks, we're not making an alias to Bob here, right? This is okay. And the reason it's okay is that we're passing only sendable types into this method. If we wanted to pass something that wasn't sendable, if we wanted to pass a mutable object into that method to Bob, then we would be violating that isolation boundary. There's an isolation bubble there that we would be violating. But it's okay to do it here because ant is val, globally immutable. But the next one is bad, right? We can't look up Bob in that map and keep an isolated reference. Now we would have two isolated references to Bob. So that's illegal. The next one's fine. We can have a tag alias to Bob that's compatible with the isolated alias in the map. And the really important part is the last one also being fine here, where if we remove Bob from the map, the type signature on remove tells us that we're getting an ephemeral V. So in this case, V is aardvark iso, so we're getting an aardvark iso ephemeral. And when we alias it, we know that we still get an aardvark iso. And this gives us static alias tracking, which lets us enforce our deny guarantees and lets us do it with local reasoning only, right? We don't need a big global static analysis pass through the program. We can do it all through local type checking. So, Pony is formalism at the root. There's been a tight feedback between research and development on it. I say here that the formalism has improved the implementation. That's absolutely true. The implementation has improved the formalism. More true than I thought it would be, actually, in the beginning. There have been several places where we've found that a performance optimization turned out to be a fundamental change to the formalism. And I'll talk about a little bit about that in talking about the garbage collector. So this does mean that Pony has an actual operational semantics. This is the operational semantics modulo pattern matching. So the pattern matching hasn't been formally specified yet. And a formally specified type system. We have a hand proof, not a mechanical proof, that the reference capability system is sound. Hopefully we'll get a chance to do a mechanical proof on that as well. So, leveraging the type system in the runtime. So for me, as a software engineer, I've come kind of late in life to computer science, to be honest. But as a software engineer, I've been very performance focused. And it turns out that type systems, far from being a matter of correctness, in my mind, are a matter of performance. That not just the guarantees that you can make at the program level, but the guarantees that you can make at the language level, the changes you can make in the actual language runtime because you have enforced certain type system properties. And for Pony, the interesting one is data race freedom. And so in the runtime, what can we make faster due to data race freedom? And it turns out basically everything, right? This is a catalog of the runtime. There's a few things that aren't in there, but nearly everything. The actual underlying runtime implementation is directly influenced by the type system, which is fun. I'm going to mostly talk about garbage collection. That's what we've been publishing papers about. There's some very interesting stuff in the other elements, but I'm going to concentrate on this. So we're going to start with per actor heaps like Erlang. That's good. We can use a mark and don't sweep collector. That's super efficient, right? We're not going to ever touch unreachable memory when we do a sweep phase because we don't have a sweep phase. That's great. Non-incremental, non-generational, non-copying, that's a lot of overhead that we don't need because we're collecting individual actor heaps, which means we have in a system that typically you can run million, 10 million, 100 million actors in a single program. You get incremental and generational collection essentially for free by having per actor heaps. But now we get into the really fast stuff. No read barriers, no write barriers, no card table marking, no pointer fix-ups. This is a lot of overhead that traditional garbage collection systems have. And as long as we can deal with the fragmentation problem, which we do in the underlying pool allocator, saving on this is a huge win for performance. But if we have data race freedom, we want to be able to pass references between actors by pointer. We don't want to copy them. If we copy them, essentially we've given up all the performance benefits that we get out of per actor heaps. So how are we going to prevent premature collection when we do that? And how are we going to do it without synchronization? And that means also no round-trip messaging, right? As soon as you have a round-trip message, you have a form of synchronization. We don't want that. We don't want that level of coordination. So what we have is a protocol called ORCA, which is object reference counting for actors. It's a variant of deferred distributed weighted reference counting, but every time I say reference counting, I feel like I really have to clarify that this has nothing to do with the shape of the heap. So if you do assignments in the heap or mutate an actor's heap and change the shape in any way, that doesn't change reference counting. Reference counts only change when you send and receive messages. Okay, how it works. So when an actor sends a reference to an object that it has allocated, it increments its local reference count for that object. It knows that somewhere out there, somebody might have a reference to it. It doesn't know who, and that's important that you don't have to keep track of who, but it knows that it's been done. Similarly, if you get one back that you allocated, you decrement the local reference count, right? And those work exactly in reverse if it was allocated on someone else's heap. So if it's allocated on someone else's heap and you receive it in a message, you say, I'm the receiver of that incremented reference count. I'll pop it up by 1. And when I send it away, I'll lower it by 1. I've given up a reference. Okay? So the core... Sure, yeah.
So when an actor receives, in this number 2, when an actor receives a message to one of its own objects
yes.
in a message.
Yes.
Okay. Then it decrements its own reference count.
Right.
And then was the third bit. So that means that if a remote actor gives up a reference, it must send it back whence it came. It can't just let go of it.
It doesn't. Actually, it does. It just lets go of it. Sorry, I was misleading there. I apologize.
How does the original guy ever get to hear that it's been decremented?
Fantastic. That's this slide. That's exactly the perfect question, because it's actually, there's two core problems in there. Not only how do you get to know that it's been decremented, but what do I do if I want to send a reference to a remote object and I've run out of references? If I receive it once and I want to send it twice, or if I want to send it once and keep a reference in my own heap, what do I do? Because I need to be able to invent a new weighted reference count to it, and I need to be able to do that without a round-trip coordination step. So what ORCA does is it says, we're going to leverage the fact that on a single node, messaging is causal, right? In other words, if A sends a message to B, and then A sends a message to C, if in response to the second message, C sends a message to B, it's guaranteed to arrive after the first message. And that's trivially done on a single node for free. It actually has no runtime cost. In a distributed system, we'll see that this would be a very bad idea to rely on, and there's an extension to the protocol. In a distributed system, relying on causality leads to tree-structured networks and O log n latency, which isn't the worst thing in the world, but it isn't great. So we can do this without causality in a distributed setting. So we're going to leverage that. And so what we're going to do is, when we want to send out a reference to an object and we've run out of local reference count for it, we're just going to invent some. And we're going to send a message to the owner saying, we've invented this many references. And we're going to send it before we send the follow-on message, the actual message that we intended to send in the first place. And what that means is, if the destination actor of our message sends a decrement message to the owning actor, it is guaranteed to arrive after our increment message. Okay? So that gets to the second part of that question. What do you do when you no longer reference an object? That's fine. You detect that during garbage collection of your local heap. You say, oh, look, I have some reference count for stuff that never appeared in my heap. I never marked it. So I'm going to generate decrement messages to the owner.
Just to double check, so
Sure.
you rely on is that all messages from a single actor are received in sequential order.
Yes.
When they are compatible with the centers.
Yes. Yeah. Which it turns out is again, this is about this confluence of the type system and the runtime, is actually free to implement on the runtime. It's literally zero runtime cost to implement that guarantee. And I'll cover the changes for distributed garbage collection in a little bit, because that's a very good point. All right, so these are the invariants. The local reference count and the ORCA message count, which is to say the collection of increment and decrement messages for some object, are always balanced by the foreign reference count, right? The local reference count being the actor that allocated the object, and the foreign reference count being all other actors. And the application message count, which is to say how many messages happen to be out in the wild that contain a reference to this object. And that always holds. And it means that in the presence of a data race-free type system, and only in the presence of a data race-free type system, we get this cross-actor, cross-heap garbage collection with very cheap amortized messaging, with no coordination phase, which is fun.
It's the usual cycle thing with reference counting, isn't there?
Yeah, what a great question. So I'm going to cover that when I talk about collecting actors, but I'll talk about it a little bit here. For collecting passive objects, the objects don't act, because the shape of the heap doesn't influence reference counts, objects don't have reference counts for other objects. Only actors have reference counts for objects.
Objects do not have reference count for other objects.
Right. Because just because I've assigned something to the field of the object doesn't change its reference count. It only changes if it's sent or received in a message. That's an excellent point, because having a cycle problem with reference counts would, of course, make this incredibly slow and basically useless. But because we don't have any cycles on reference counts, we don't need any kind of cycle breaking or cycle detector or anything for collecting passive objects. But you're absolutely right that there is a problem. And the problem is going to come on this slide. Just one more forward. So yeah, so this gives us this no stop the world GC for passive objects. And I'll cover why it works for actors in a minute. So the combination is we get rid of all of those GC overheads, and we have no stop the world phase. And when you do benchmarking, boy, getting rid of that stop the world phase and getting rid of those hard old generation collections and getting rid of card table marking, pointer fix-ups, this makes a huge difference for performance. But let's get back to this super important point. if we're going to collect objects like that, how are we going to collect the actors? Because we don't want a system that says you have to manually manage actors. Admittedly, in other actor languages, you do have to manually manage actor lifetime. You have to send them poison pills. You have to keep track of when you might black hole messages. It can get very complex. But we want a system that can determine when an actor not only has no work to perform, but will never have work to perform in the future and automatically garbage collect those actors, because we want nice, safe semantics. So to do that, we need a cycle detector. And the reason is exactly your point about as soon as you have this reference counting situation between actors, now A has a reference to B, B has a reference to A, what are we going to do? We can determine that they've blocked, but their reference count is never going to drop to 0. So we need to introduce a cycle detector. And in Pony, that's an actor. The cycle detector is itself an actor, and it detects isolated graphs of blocked actors. The problem is that topology is always out of date. And it's not just out of date, it's really extra out of date, because when an actor blocks, it reports its own view of its topology to the cycle detector, right? So the cycle detector's view will be out of date compared to the actor's view. But the actor's view is quite likely out of date with reality, because it's not going to actually examine any message queues or any other actors. It's just going to look at its own topology as it sees it in order to report it to the cycle detector.
And does that whenever it blocks?
No, because obviously that would be a problem. So when an actor's message queue is empty and it gets rescheduled and it's still empty and it can successfully mark its message queue as empty by setting a low bit in the queue, which means that no one else has posted a message in the meantime, only then will it report to the cycle detector that it's blocked.
Okay. So if it's been blocked for a while, is what it amounts to.
Yeah. Two schedulings turns out to be an okay heuristic. I think it actually needs a little bit of improvement. There are cases where you get too many block messages. It's very artificial benchmarks that do it, but I think those artificial benchmarks might have some real-world use cases. So what we want to do is verify that the topology that the cycle detector received was correct at the time that it's sent. So what we're going to do is we're going to have this confirmation and acknowledgement protocol that we build on top of the cycle detector. And it's very simple. When the cycle detector perceives an isolated graph, it sends a confirmation message to every actor in that isolated graph with a token that's just a number that happens to indicate that perceived cycle.
Oh, wait, sorry. How does it perceive the graph at all?
So it does it on the basis of the out-of-date topology that the actor reports when it blocks.
The actor reports something.
Mm-hmm. It says, here's what I think my reference count is, and here's what here are the reference counts I believe I hold for other actors, which turns out to be a nice compact data structure. It's inevitably, mostly, a wrong data structure. So what we need to do is, once we have an isolated graph, determine whether or not they were correct at the time they were sent without reasoning by time or doing any kind of rewinding or anything like that. So what we do is we send out this confirmation message, and it says, I want you to confirm number 9, just some number that uniquely identifies the token. It's actually just a monotonically increasing number. When an actor gets a confirmation message, it just echoes back an acknowledgement message with the token, nothing else, no logic. And importantly, it does not consider itself unblocked if it receives a confirmation message. Right? Any other message unblocks the actor, but a confirmation message doesn't. The fun part here is that when a cycle detector receives an acknowledgement message from an actor without having received an unblock message in between, then we can prove that not only is the cycle detector's view of that actor's topology correct, but it was correct at the time that it was sent, which is pretty fun. So not only have we done queue clearing effectively in a software engineering sense, but in a proof sense, we know that this topology was correct at the time it was sent. So once we get an acknowledgement message back from every actor in the isolated graph, we know that the topology for the entire graph was correct at the time it was reported, and therefore it's a true cycle, and we can collect it. Okay, so why is this efficient? The number one reason is that messages are cheap. So sending a message in Pony is a single atomic operation, which means you're talking about, depending on your platform, 5 to 15 nanoseconds of overhead for sending a message. The second is block and unblock messages are processed in a deferred manner by the cycle detector. That's really important. If you do too much work on every block and unblock message you receive and you try and detect cycles every time you get a change in topology, then you weigh down the system. But if you treat it as exactly what it is, which is a garbage collector, and say that it's not important that it runs now, it's just important that it runs, then you can do this in a deferred way. And there's a core problem you may spot there, which is what if no more messages are generated and you've deferred? And the answer is that it turns out that scheduler threads are actors too in Pony. And when all of your scheduler threads are blocked, they send each other messages in the same conf-ack protocol to do quiescence detection, so that your scheduler threads can quiesce before the cycle detector has collected all actors. So it's truly just garbage collection, not termination, that we're doing with the cycle detector. And termination can be done by scheduler quiescence and happens nice and fast. Yeah?
You're right that the cycle detection is essentially sequential.
I'm sorry, can you say that again?
So the cycle detection is essentially a sequential process?
Yes, it is, exactly. So that's a very, very important point. In Pony, actors are non-pipelined. So every actor behavior, every time it handles a message, that's a logically atomic operation. It can't witness any mutation during that behavior that it has not itself performed. And it won't start handling a new message until it's finished that logically atomic behavior. Yeah. And so it turns out all the overhead from manually managing actors is, generally speaking, more expensive than doing this automatically, compared to manual actor management in Erlang or Akka or other languages. So, development status. Everything so far, that's all real, right? This is in use, this is in production. We run on lots of machines, Raspberry Pis, 4,000-core SGIs. Mostly, to be honest, 64-core Xeons is the usual deployment platform. Windows, OS X, Linux, FreeBSD. Mostly developing on Windows and OS X and deploying on Linux seems to be the pattern in real-world use. Performance is competitive with C and C++ on a single core, and often significantly better as core counts go up, and we have nice actor model algorithms that scale well. One of the big advantages of having a native language is that we actually can exceed C performance for most sequential algorithms. And the reason is entirely down to register allocation. To some degree, it's a question of inlining and other compiler optimizations, but register allocation turns out to be a huge one. Being able to do register coloring across a much larger set of code. So let's talk about the distributed work. This is what I'm actually working on now. This is the stuff that's not done. One of the most important things in the design of Pony is making sure that the distributed semantics are the same as far as the programmer is concerned as single node semantics. We don't want the programmer to write a program and then say, okay, now I want a distributed version, I have to write a new program, essentially. You want to say, I wrote a program, I'm going to run it on a single core, I'm going to run it on 4,000 cores, or I'm going to run it on 4,000 nodes, and do it all with the same program, source code-wise. So what changes when we go from one node to many nodes? Okay, one of those is a type system for machine-specific data. It's absolutely fine for me to send a 32-bit integer to some other actor, right? That's an immutable value, no problem. What if it's a file descriptor? Now we have a problem. So we need to extend the type system with the concept of machine-specific data. We also need a concept of node failure, right? On average, in a distributed system, you have failed nodes. What's the chance of a failed node? 1. Distributed GC. There's some modifications for collecting actors in a distributed setting. It turns out we can collect objects in a distributed setting without modification, which is interesting. And then there's distributed work stealing. How do we migrate actors? How do we know it's a good idea to migrate an actor to another node? So the machine-specific data stuff is pretty straightforward. A type system annotation can mark an individual reference as machine-specific data. You say, okay, this is a file descriptor, that's fine. And what that does is pollute any type that has that as a field. That then becomes a machine-specific data type. And you can only send machine-specific data types in messages to local actors, actors that you can prove not only are on your node, but will stay on your node, because it's no good sending a file descriptor to an actor that then gets migrated onto another node, right? Or an OpenGL handle or anything else that's machine-specific. So those two annotations work together pretty well.
Wouldn't it be more common to keep the file descriptor in one actor and
Yes.
send messages to the actor?
Absolutely, yes.
So it seems a bit funny as soon as you've got two actors with the same file descriptor or the same OpenGL, WinWAR,
It would be
now you're
terrible.
into a whole lot of pain about race hazards and so forth, aren't you?
Absolutely. And
So why not just not do that?
because how can you prove that you're not doing it?
Suppose you could take any bit pattern, and it depends on your language, right?
Right. So what I want to do is prove statically ahead of time and be able to show the programmer that they can't do this bad idea.
Oh, I see. So you're going to prevent people doing that?
Absolutely.
Oh, okay. I thought you were going to send these things from one to the other.
Well, it turns out you can under some circumstances, and in some cases, perhaps someone's going to get some use out of that. But the primary purpose of this type system is prevent you from doing exactly that.
Oh, okay. No,
Yeah. Yeah. It turns out there's some...
Something about sending it to another thing on the same machine. Oh,
Right.
no,
So proving that you can do that turns out to be, yeah, okay, there are cases where you can prove that that would be acceptable, just really bad programming practice, but won't cause a problem. But the purpose of the type system is prove that I haven't accidentally done that in the distributed setting. Yeah. So showing locality. This is about permanent locality, right? And this means you can do things like have an actor that manages I/O, and it's permanently resident on a given node. And then we have some interesting concepts about I want to be able to log to that actor. Okay, well, what sorts of things can you log to the logging actor if you're running on another node? Well, you can't log machine-specific data because it's running on another node. But you could log machine-specific data if you were running on the same node, but again, why would you do that? The point is to make sure that you don't accidentally do it. Node failure. So your nodes are down, right, by definition. So there's been tons of research on approaches to this. There's really great work out there. There's stuff on orthogonal persistence, and it turns out we're just going to copy Erlang. It's a little bit different from Erlang because Erlang actors fail for all kinds of reasons because it's dynamically typed, and Pony actors only fail when the node explodes, right? I was talking to Joe Armstrong at a conference in November at CodeMash in London, and he says, your type system is really fun and it's really interesting, but how does it protect against a lightning strike? And I thought that was a great way to talk about node failure. And the answer, of course, is that it doesn't, and you need monitoring and you need supervision. The fun part is when you can expand that to a type-safe language, it means that if you've registered to be notified when some actor disappears, you know it's only disappeared because there's been some kind of hardware failure, whether that's a network partition or an actual node failure. And that means that how you carry on from that point is really an application-level decision, which is pretty neat. It means that if you have a network partition, the application can decide whether it wants to carry on, given that it can no longer reach this set of actors, or in what manner it's going to carry on. And in some ways, that's punting and putting the problem on the programmer. But actually, hopefully, what that really is a much more flexible approach that says you can design a recovery strategy that's specific to your application. So distributed object GC. Turns out, because of a data race-free type system, you get this almost for free. Every node can collect passive garbage locally on that node in the same way it would if it were a single node program. Because if I send some isolated data to some other node, well, it has the one and only copy of it, right? So it's fine. It can manage collection on its own. If I send immutable data around, if some node collects its copy of the immutable data, that's fine. I've still got mine. And if I send it in the future, that's fine. It'll just get a new copy. So that's pretty neat. But what it doesn't do is preserve global identity. In the timers example, if I were to send some timer to the timers actor, and then I want to keep a tag and I want to send it again, wait a minute. Who's responsible for managing that identity and making sure if it's collected on one node that we still have an idea that it's the same identity later? And it turns out that's not that bad. It's just a question of keeping monotonic global identities when you send objects and keeping a map in your distribution actor of real addresses to global identities. So distributed actor GC, this is where the real extension is needed. It's not as bad as you'd think. When I was first putting this together, I thought we needed to maintain causality in a distributed setting. That would be bad. We put a lot of work into that. We came up with a system that is kind of neat in that it has O log n latency with no extra space complexity. So that's pretty good. But it's much better just to be able to get rid of it entirely. And it turns out the only thing you need to do is introduce one new message and one new mapping. And it's a mapping of node to an actor reference count. And it boils down to when some node sends a reference to a remote actor, to a third-party node, before it sends that, it sends a shift message to the owning node, the allocating node, that shifts one RC from the sending node to the receiving node. Now, as part of that, I might also invent some new reference counts or any of the stuff that we've talked about previously in the protocol. And the key is that there's a new invariant, which is that all of those node RCs have to balance as well in order to collect an actor. And this means we can do it without any causality guarantee. Now, you still need FIFO ordering between nodes, but that's OK. We can have pairwise FIFO ordering is OK. That's cheap. So distributed actor cycle detection. Because we're running a cycle detector on each node, right? So how are we going to detect a cycle of actors that spreads across a cluster? And it turns out this is another confac problem, and it's an eventual consistency algorithm, effectively. In fact, all of the confac protocols are a form of eventual consistency algorithm, which is if we detect an isolated cycle modulo cross-node references, then what we can do is inform any other nodes that we reference from that isolated graph. We don't need to know who comes into it, only what comes out of it. We can inform them that this portion of that cycle has blocked. Here's a perceived cycle I have detected. And not only detected, but have confirmed locally, because you don't want to generate that network traffic unless you really need to. So once you've confirmed it locally, you can start spreading it around. And it turns out that is a very simple way to eventually propagate the information of all of the separate local blocked isolated graphs to each member of the cluster. And they don't even need to do it pairwise. You can just in any order and eventually collect them.
So there was a sort of monitor for detecting these cycles. So you call it the
cycle detector.
Is there still just one?
No, there's one on every node. Right, exactly. Because if there was just one, it's a huge bottleneck and it's a failure problem. Yeah, but by having it be, sorry, I'm on the right side, good. By having it be per node and having this eventual consistency algorithm that collects that cycle information, you get rid of the bottleneck. And if a node fails, you can simply say, oh, well, those actors on that node have implicitly, permanently blocked. They won't be generating new traffic as far as I'm concerned. So those nodes can be considered blocked, so we can actually carry on and collect actors that would otherwise be in a cycle with unreachable actors.
So do each of the cycle detectors on each of the nodes sort of compute some, are they all doing the same thing?
No, they're each only doing cycle detection for the actor. That's an excellent question. They're only doing cycle detection for the actors that are resident on that node.
Any cycle, but those cycles might be spread across many nodes.
Right, but what they'll do is they'll only do cycle detection for the portion of the graph that's present on the local node. And if that portion of the graph is blocked and confirmed that it's blocked, that's when it starts informing other nodes that graph references that isolated graph has blocked, and here's the set of blocked things that I've discovered.
Okay, so they sort of gossip among each other.
Exactly so. Yes, perfect.
That sounds quite complicated. Like, you haven't really explained that. So you worked all that out and...
Yes, strangely, it's not nearly as complicated.
That's a seriously tricky distributed algorithm.
Yeah, it's perhaps. So far, yeah, but so far so good is my answer to that one, which is that not only does it seem to be pretty easy to reason about, but it seems to be pretty easy to implement. Because the key is that the other nodes that a graph references are immediately available from the topology of the graph, because you have some dangling references out of the graph. So if you had to keep track of any reference into that graph, it would be a horrendous distributed computing problem. But because all of the information is available locally, it turns out to be pretty straightforward so far. But yeah, I think skepticism is well warranted.
Pretty impressive.
Well, I hope.
Because it's kind of distributed algorithm to do distributed cycle detection.
Yes, exactly so. Yes.
Did you formalize it and produce some kind of proof that it works?
Not yet. That's not formalized yet. So that's one of the things that we're working on right now at Imperial. Yeah. Right, distributed work stealing. So this is actually the hardest part. All of the other parts are pretty straightforward in that, well, straightforward, in that once you have an approach to it and you've formalized it and you know that it works, then you can implement it and everything's fine. But distributed work stealing, there isn't an optimal approach. There's no way to know. For example, so this example is my favorite example. If an actor has a large working set, right, it references, let's say it references 10 gigabytes of memory. You obviously don't want to migrate that to another host, right? Because you're going to have to serialize 10 gigabytes of memory to migrate that actor to another host. Except, one of the reasons you have a large cluster is to spread memory load across machines. And maybe exactly what you need to do is get that 10 gigabytes over on some other machine to free up memory locally. And that's a hard decision. That's a hard heuristic. So in the first version, what we're doing is allowing programmers to manually place and migrate actors. And I don't think that's ever going to go away, because I think there's an amount of domain knowledge for the application writer that isn't going to go away, where they may be able to just know better than the heuristic is ever going to know. But I really hope that we get some heuristics, and there's some work in particularly Charm++, which is a supercomputing framework in C++, on some heuristic estimates that seem pretty interesting. And it has to do with a combination of statically and dynamically figuring out sets of communicating actors, that it's communication probably more than CPU load and memory usage that should drive the migration heuristic. So, right, the future of Pony. The future of Pony is distributed computing. Whether that's small-scale IoT devices talking to each other, or large-scale supercomputing clusters, or what it's really going to be, more likely than anything, is things like Azure and EC2. So, formal work in progress. Obviously, continued formalization work with Sofia Drosopoulou at Imperial. The ORCA protocol, that's actually finished formalizing now. Formalizing the RCAP interaction with algebraic and parameterized types is work that's ongoing by a master's student at Imperial. Simple value-dependent types. Currently, Pony does not have a dependent type system, but we're going to have a very simple value-dependent type system. More similar to C++ templates than a real dependent type system at first, and see where we can go from there. The other is formalizing capability-secure reflection, which becomes quite interesting. The machine-specific data, the distributed object identity, and the GC extensions. The implementation work, the distributed runtime obviously dominates this. But other stuff that's really interesting in there is things like hot code loading. Erlang has this great system. It has its flaws, but it's very powerful, of being able to update the code in a running cluster incrementally across the cluster. We want to be able to do that. Doing that in a type-safe, ahead-of-time compiled language is interesting. It turns out it's probably the same problem as the REPL. So that's interesting. Auto-formatting, self-hosted compiler, all the usual goodness that you eventually want. Currently, the compiler is written in C for bootstrapping reasons. So, we have a community. It's growing. It's still very small. But we do have sort of about 50 different people contributing to the compiler and the runtime, and we have a collection of companies that are implementing things in Pony. Most of them are in the financial industry, interestingly, ranging from financial startups, fintech startups in New York, to tier 1 investment banks who have rolled out global products. That's been an exciting way to validate that something works, is to deal with $10 billion of flow a day. Great, thank you very much, everybody, for coming. And any questions, I'll be happy to try and answer them. Yeah.
So one question you have to think about in these things, when you've got the ability to either, I guess, serialize the structure and send it in a message to another actor, in which case it takes a copy,
right?
Or you could sort of send a pointer to it somehow,
right?
And the programmer specifies that, do they somehow?
No, the language handles it. So if you're communicating on the local node, it'll always be by pointer, and it'll only ever serialize if you're sending across to another node.
Okay. Huh.
Yeah, because you never want to serialize locally. If you
you won't want to send to another node not serializing precisely. Oh, I guess.
But then what you can do is you can
distributed reference counting thing, right? That was the whole point. You might want to send a reference rather than sending your gigabyte object to another.
Right,
You might want to send a reference, so maybe so it can send it back. I don't know.
Yes, exactly. So it turns out that's an excellent question, because what you can do is you can use the tag capability. Because the tag capability says this is identity only. I'm not interested in the contents. You're not going to be able to read or write the contents, so you don't need them. So when I serialize it, I can serialize it merely as global identity. It might represent 10 gigabytes of data, but I'm going to serialize it to you as 64 bits. And you can refer to it, send it back to me in a message.
So I'm still trying to understand the boundary between what the system decides,
Sure.
or the language decides, and what the programmer decides.
All of these are defined. So let me back up there. The programmer decides that by the type that they indicate is being sent in the message.
Okay.
If they send something that's readable or writable, then that data must be available to the receiving actor. But if they indicate something that is neither writable nor readable, then that data need not be available. So we can skip serializing it.
So for the type system, so the guys in Microsoft who had this type system, they had a back door where they kind of did unsafe stuff repeatedly.
Yes.
Do you end up needing that at all, or is?
I'm going to go with so far so good. So far we haven't. I'm not going to guarantee that that's going to hold. If it doesn't hold, I'll be very sad.
So one of the use cases they had where they needed it was when you have some distributed computation where you're trying to find a minimum solution, and if you go above that count on your particular search, then you want to kind of say, well, I don't want to carry on, and then you want to inform other people when you find something better. And then, so like I guess finding the shortest path, if you've got multiple actors going out trying to find it, you want them all to kind of know the best so far.
You want them to be able to incrementally report a best case, and if they find something better than the last best case that they've received, they want to be able to broadcast that to the set of actors.
But then the broadcast is going to be expensive in comparison to using mutable state.
Right.
So
if you go the mutable state approach, then what happens is you can possibly get a performance improvement depending on how you build the algorithm. Or what you can end up with is a big problem once you go distributed, because that mutable state now needs to be tracked in a distributed way. So the Pony approach to that specific problem, because it's essentially one of the stream processing problems, and there's a fintech company in New York that's building a stream processing system on top of this. And it turns out their approach is to say, to treat it much more as a data flow problem. Everyone says reactive now, so I'll say reactive. So to say that when you find a solution, what you're going to do is, maybe you have a last known solution, but maybe you don't. Maybe you don't even keep track of a last known solution. What you do is you flow it through a local actor that keeps track of last known solutions. And then it makes the reporting decision. And because we have that free send to a local actor, right, you're just passing a pointer to it, and it can mutate this. And now you have constrained your broadcast problem quite a bit. You have one message per node instead of one message per working actor. So far, what we've seen is changing the algorithm has been better than violating the isolation. But definitely that's so far. All right. Anyone else? Okay, thank you very much.